We're going to finish up the problem that we started in our last video. We're going to be working with the exact same function, and what I'd like to do this time is to work with the critical point that we found in that last example and to talk about, well, do I have a local maximum, do I have a local minimum, or do I have a saddle point at this particular critical point? Now, in order to do that, I'm going to have to check the sign of a few different values. Those are going to come from some second order partial derivatives. So here A is the second order partial derivative, first with respect to x and then with respect to x again. B is the second order partial derivative, first with respect to x, then with respect to y. And then finally, C over here, I've got the second order partial derivative, first with respect to y, and then with respect to y again. So I'm going to have to find some second order partial derivatives. In order to do that, I should find some first order partial derivatives. So I'm going to look at my function to start off. Let's find the first order partial derivative with respect to x. So the derivative of x squared would be 2x. Derivative of xy with respect to x would be 1 times y, or just simply y. Y squared is a constant with respect to x. Derivative of negative 7x would be minus 7. 4y and 9 are both constants with respect to x, so here is my first order partial derivative. So there is that. I'm going to use that to help me find a couple second order partial derivatives. So first, I'm going to find the second order partial derivative with respect to x again. So derivative of this function that I just found with respect to x, derivative of 2x would be 2, and then y and negative 7, those are both constants with respect to x, so their derivatives are 0. So here's my first second order partial derivative. I'm going to come back to that towards the end of my problem. I still need to find a few more. So next, I'm going to go ahead and work towards, this isn't exactly b, but I'm going to work towards finding b right here, which, if I look at this, the partial with respect to x, which I already have, and then with respect to y. So working with this same function right here, I'm going to find the partial with respect to y this time. So derivative of 2x with respect to y is 0. It's a constant. Derivative of y would just simply be 1, and then negative 7 is a constant, so its derivative is 0. Here is my next second order partial derivative. I do have one more to go here. If I scroll back up, I need to find the second order partial derivative, first with respect to y, and then with respect to y again. So back to our problem, looking back at our original function right here, I'm going to find first the first order partial derivative. So the derivative of x squared with respect to y would just be 0. It's a constant. Derivative of x times y would be x times 1, or simply just x. Derivative of y squared with respect to y would be plus 2y. Negative 7x is a constant with respect to y, so its derivative is 0. 4y, its derivative would be plus 4. And then 9 is a constant, so its derivative is 0. So here's my first order partial derivative. I'm going to use that to help me find my second order partial derivative. So I'm going to take the derivative with respect to y. I'm looking at this point right here one more time. So x is a constant with respect to y, so its derivative is 0. Derivative of 2y would be just simply 2. And 4 is a constant, so of course its derivative is 0. So here is my last second order partial derivative that I needed. So at this point, I have everything I need. I now need to, now this might seem a little bit silly because all of these second order partial derivatives that I found down here are constants. But my next step, I need to evaluate each of these second order partial derivatives at this a comma b, which is our critical point. So just to show what this would look like, I would be taking the critical point, which we found in our first video, and plugging it into each one of these second order partial derivatives. Now again, this is going to perhaps look a little bit silly, but I should go through it. Taking 6 comma -5, plugging this in, plugging x equals 6 and y equals -5 in. It seems silly because, well, there's nowhere for me to plug it into. It's just a constant function, which is always equal to 2. So next, okay, let's go ahead and do the same thing with that middle second order partial derivative, plugging in 6 comma -5. Once again, I just have a constant function, so it's just going to be 1. And then finally, for my rightmost derivative, plugging in 6 comma -5, I just get back 2. There's nowhere for me to plug these values into, so it's just simply 2. So what I found at this point, this is a value I'm going to call capital A. This value in blue, 1, is my capital B. And finally, whoops, this value over here, 2, that is my value for capital C. I now need to look at the sign of these, or the sign of some expression of these, and that is what will inform me what the behavior is at this particular critical number. So if I scroll back up and look at this handy-dandy table that I have here, the first thing that I'm going to look at is this sign of AC minus B squared. I'm going to check that first. So I want AC minus B squared. Let's look at that first. So I want A times C minus B squared. I am most interested in the sign. So A is 2 times C is also 2 minus B squared, that is 1 squared. So I have 4 minus 1 simplifies to be 3. So that is a positive number. So 3, which is positive. Well, I have a positive for the first. So it could be either one of these two cases. So it could be this case or it could be this case. So the next thing that I need to check then is what is the sign of A, because that's going to tell me whether I have a local maximum or whether I have a local minimum. So if I check the sign of A, scroll down one last time, whoops, A is 2, which is positive. So we know that A is positive. We scroll back up one final time. We know that A is positive, so we are looking at this row right here. That means that we must have a local minimum at our critical point. So to finish this problem up, our critical point was, of course, right here, 6 comma -5. That means that 6 comma -5 is a local minimum of our function f of x, y. So there is our behavior at that particular critical number. If you want to copy this table down, I do think that it is pretty helpful to have in your back pocket as you're working through these problems, just as a way to quickly identify the behavior at these. It's a lot of finding second derivatives and then evaluating them at these points, but as long as you take your time and you go slow with these problems, you will end up with the correct solution.